Okay, so let's start off with classifying reactions. And so it's going to be kind of clunky getting used to how to recognize these things, but the more we practice, the better we'll get. And so what I'm going to go through with you guys is we're going to identify some patterns that will help us in classifying reactions. So how many reactants and products do they have? What type of reactants and products, and so forth. So we're going to take some notes on the 5 different types that we're going to cover and what those things, little patterns that we can pick out. So we're going to start with the first one, which is combustion. Now for combustion reactions, I have 4 examples to the left here. You might start seeing a pattern where we have some sort of amount of carbons and hydrogens as the reactant. Sometimes they have oxygens in them as well. So we're going to say that generically, I'm going to just say CXHYOZ, where the X, Y, and Z could be any amount. It could stand for any whole number, just like how we do quantities of our atoms. And so any sort of generic carbon hydrogen reactant that is present. What is the other thing that's present here? So you guys probably see that there's oxygen. Well, just like you need oxygen for a fire to happen, think of combustion as a big explosion. In order for these things to occur, we need oxygen input. And so remembering oxygen is diatomic, that's why we write it as O2. You need to have O2 as a reactant. And the other nice thing that you have to have, which is consistent throughout, is then you're going to get the same products for every reaction. You're going to have carbon dioxide and water. So we'll note that we have CO2 plus H2O products. So combustion, you have to have O2 as a reactant. These are going to be your products. All right, so the second one that we're going to talk about here is called synthesis. And you can think of synthesis, you're making something. So just like how you put a bunch of ingredients together to make pancakes, kind of the end that you get for synthesis here, where you're going to have 2 or more. So in this case, there's about, for my 4 examples, I use 2 reactants, but it can be more. So we're going to write 2 or more reactants. And these are going to form just one single product. So in order to be synthesis, you have to have only one product. That's important. All right. And then if you guys also have questions throughout any of this and don't feel like voice chatting, you can also just send me a chat over Zoom. All right, let's talk about the next one here. This is going to be decomposition. Oops. And so you can think of decomposition as decomposing. If you decompose something, you break it into little parts. So this is the reverse of synthesis. So now you only have one reactant that creates 2 or more products. So if we look on our examples, we have a mercury oxide that forms mercury and oxygen gas. Water can decompose until it's into its elemental parts of hydrogen and oxygen, and so forth. So we have one reactant and 2 or more products. Now, the last 2 we have are probably the more complicated ones, but they're still not too bad. It's like I said, it's going to feel a little clunky, but more practice, the better. And so the second to last one we have here is called single replacement. So in single replacement reactions, let's start kind of seeing what we can observe. I'm gonna use different color highlighter to try to emphasize this. But if you notice, there is a single element on the reactant side for every single one of these questions. And then there's a different type of single element on the product side. And so what we're getting is an element plus some type of compound, which is producing a different element and a new compound. And so instead of making notes like how we've done before, I'm going to write a generic reaction equation for this. So we're going to have an element plus a compound. This is going to create a different element with a different compound. So this is just in comparison to what we started with. So again, for example, the last one, zinc would be our element. Hydrochloric acid would be our compound. And after they react, we create a new compound, zinc chloride. And so this would be our different compound, and our different element would be hydrogen gas. All right, then we have double replacement. And so for double replacement, you're going to have a total of 4 different compounds. And so if we break this thing down, we have for example, for the first one, potassium hydroxide, we have a sulfuric acid here, and then we have potassium sulfate and water. So we have 4 different types of compounds going on here. Now, the way that I'm going to write this is similar to above where it's generic, but we have a compound plus a different compound, which then creates 2 different compounds. So there's no elements as reactants or products in a double replacement. Now, I give these reactions a nickname. So I also call them double rainbows. So double replacement, double rainbow. I will show you why. So if we think about the 2 different parts that make these things up, I'm going to use the bottom one as an example. So we have our silver nitrate and our sodium chloride. Those are our 2 reactants. If we draw an outer rainbow to the outside parts, so we have silver and chlorine that buddy up, and then an inner rainbow between sodium and nitrate, those are the products that form. So we have a silver chloride complex as well as a sodium nitrate. So I call it double rainbow because this is actually the pairs that occur after the reaction. So they kind of switch partners. So I call the double replacement my double rainbow method because you can predict the products just from the reactants. All right, are there any questions on classifying before I move on to balancing? Awesome. Okay. Let's talk about balancing. So hopefully this should be a refresher. And now one thing I want to throw the caveat out there. You guys may have learned to do this a slightly different way. This is just how I do it. If you do it a different way and it works for you, totally fine. We just want to make sure we're getting to the right answer. And so number one thing for all of science, I want you guys to remember, is the law of conservation, which defines that matter cannot be created or destroyed. This counts for atoms, this counts for materials, energy. electrons. We can't just create or destroy these things. They have to go somewhere. And this is the basis of why we have to make sure to balance our chemical reactions. This is our duty as scientists. And so the way we do so is we use coefficients. And just a reminder on what a coefficient is, if I were to put a 2 in front of the formula H2O, this 2 would be a coefficient. This one would be a subscript. So it's just a reminder. All right, so we make sure that these coefficients are also the smallest whole number ratios. And so what I mean by that is if we get coefficients that are 2, 2, and 4, that is incorrect because we can divide all of them by 2 and get 1, 1, and 2. That would be the most correct form. So always double check if you can divide everything by the same number, do it. And so just going over a few rules on balancing, we count the number of atoms of one individual element on the reactant side, and we count how many there is on the product side. We do this for all elements present on both sides. Then when we start deciding that we want to change quantities, you write coefficients one at a time. Otherwise, things can get too complicated. Then you'll retally the atoms that you changed and carry on. Now, I can't emphasize number 3 enough. We can only use coefficients. You cannot change chemical formulas. So just how I did 2H2O, that's good. You can never just change the subscript in the chemical formula. That is very wrong. Revise when necessary. So if you're still not balanced, go back, repeat the process of writing coefficients and retallying. And then this number 5, what I just went over, simplify all coefficients by the same number, do it. But let's walk through some examples. So starting off with the synthesis of water. So this is a synthesis reaction. So the way I start these problems is I like to draw a squiggly line down from the arrow. So on the left side, that's my reactants. On the right side, that's my products. And then I have hydrogen that I'm going to tally the amount of atoms. And then I have oxygen that I'm going to count up. And so I repeat that same pattern, hydrogen and oxygen on the right-hand side. So you have to make sure that you count, including subscripts. So we have 2 hydrogens on the left side as well as 2 oxygens. And then on the right-hand side in water, we have 2 hydrogens. And since there is no subscript number, we assume 1. So there's 1 oxygen here. Now, the difference here, hydrogens are even, but our oxygens are not even. And so what we have to do is put a 2 in front of H2O, because this is the species that contains our uneven oxygens. Now, you have to multiply that coefficient by everything.
Yes! I'm in it right
now. By everything that's in that species. So 2 times 2 is 4, and then 2 times 1 is just 2. So these are our new totals. Now our oxygens are good, but our hydrogens aren't balanced. So what we're going to do is find our hydrogen containing species. What times 2 will get us to 4? That's just 2. And so we just need that coefficient of 2 out in front, and we are all balanced. Now you can write a 1 in front of O2, but you don't have to, because if you don't write anything, it's just assumed that it's the coefficient of 1. All right, let's do another one. So here again, I'm drawing that squiggly line separating our reactants and products. And now we have 4 separate elements to count. We have calcium, hydrogen, nitrogen, and oxygen. And I'm going to repeat that same order so I don't confuse myself, even though it might be introduced different on the right-hand side. But visually, it helps to keep everything on the same line. So for calcium, On the left-hand side, we just have one atom. Hydrogen, we just have one. Nitrogen, one. And then we have 3 oxygens. On the right-hand side, just one calcium. But now, when we have a subscript that is outside of parentheses, you have to multiply that 2 by everything inside the parentheses. So there's only one nitrogen, but we have 2 of them because of the subscript 2. Now we have 3 oxygens, but we're multiplying that by 2. So we have a total of 6. So it's not addition, but multiplication when there's parentheses involved. And then lastly, we have our 2 hydrogens here. So the first difference I see, I usually just start from the top of whatever I start with. So calciums, those are good. Hydrogens aren't equal though. We have 2 on the right-hand side and only 1 on the left. So I'm going to find the species with hydrogen. That's HNO3. And I'm going to put a 2 in front of it. Now, if I reassess, I have 2 hydrogens, 2 nitrogens, and then you also have to multiply the coefficient out in front by the subscript. So 2 times 3. So I'm just going to put a multiplication sign to remind myself. 2 times 3, which is 6. If you look, now all of our quantities are equal. So we only have to change one coefficient for this reaction. Ask yourself, what type of reaction do you think this is? So what you should have gotten is a single replacement. Because the generic equation that we wrote for the single replacement is a single atom, or sorry, a single element in a compound, which forms a new compound in a different single element. So this follows the single replacement protocol. All right, moving on to the next one. Squiggly line, we have aluminum, copper, sulfur, oxygen. Repeating that on the other side of the line. So let's first work on tallying here. Oh, I knew I was going to erase these marks. Hold on one second here. This should be. Don't worry, it's right on your guys' stuff. I forgot to change it on mine. Anyway, so for this first one here, we have 1 aluminum, 1 copper, 1 sulfur, and 4 oxygens. On the right-hand side, we have 2 aluminums, and then if we distribute the 3 to the sulfur and the oxygen, we get 3 sulfurs, and then 3 times 4 is 12, so we have 12 oxygens here. Then 1 copper. So starting off, our aluminums are not equivalent. So I find the aluminum containing compound. I'm going to put 2 in front. Now the aluminums are balanced. Coppers are okay for right now, but our sulfurs are not equivalent. I have 3 on the right-hand side and only 1 here. So I'm going to find the one that contains sulfur. To get to 3, I'll put a 3 out in front. This now changes coppers to 3. We have 3 sulfurs, and then 3 times 4 is 12 oxygen. So if I look, the only ones that aren't balanced right now is the copper. But lucky for us, there's just a single copper hanging out by itself. So we can just put a 3 out in front. And now we are all balanced. So you should have 2, 3, 1, and 3 as your coefficients. All right, last one here. Squiggly line. We have iron, chlorine, lead, nitrogen, and oxygen. So we have 5 elements that we have to keep track of for this one. So on the left-hand side, we start off with 1 iron, 3 chlorines. We have 1 lead. If we distribute the 2, we have 2 nitrogens and 6 oxygens. Now, if we look on the right-hand side, we have 1 iron. Distribute the 3, we have 3 nitrogens. Then oxygen, 3 times 3 is 9, 1 lead, and 2 chlorines. So starting from the top, our irons are good. Let's look at our chlorines. So we have 3 chlorines on one side and 2 on the other. So the smallest multiple that they could be equivalent at is if they're both equal to 6. So how would we get 3 to 6? Well, we multiply it by 2. And so we find the chlorine containing compound and put a 2 in front of it. We now have 2 irons and 6 chlorines. Now, to get the other chlorine to 6, we have to multiply it by 3. So that chlorine containing compound, we'll put a 3 in front. We now have 3 leads and 6 chlorines. Now, during that process, what we ended up doing is making our irons unequal. So we have 2 on the left side and only 1 on the right. So I'm going to put a 2 in front of iron nitrate here. This is going to change our numbers. So we have 2 irons. Oops, I just wrote Fe. So you have 2 irons. And what you can do, if you put a coefficient in front of a compound that has parentheses already, just multiply your totals that you have for these by 2. So we know that we have 3 nitrogens from this. 3 times 2 is 6, so we have 6 N's. We have 9 oxygens from the parentheses, but you multiply 9 by 2 and you get 18. So these are our new totals. If we look on the left-hand side, next thing that we have to make sure is equal, because our irons are good and our chlorines are good, would be our lead, our Pb. So we're going to put a 3 in front of the lead containing compound here. We now have 3 leads. 3 times 2 is 6. And then we have 6 oxygens. When we multiply by 3, it gives us 18. And so that gives us a balanced equation. Are there any questions on this?